400 years or so ago, there was a big debate about what the nature of light was. Some people championed the view that light behaved like a wave. Others felt that light behaved like a particle. And this debate went on for a long time. And the evidence started to add up that light was a wave-like phenomenon, that it behaved in the ways that waves behaved. And in fact, it did things like we talked about in the last chapter. We talked about diffraction. That's something that light can do that particles can't do. But there was a problem, because as the evidence started adding up that light was a wave, there were some experiments that nobody could really explain. And then around 1900, a little bit past it, a guy you may have heard of named Albert Einstein started looking at these things that nobody could explain, and he had the idea, what if light were actually a particle? It turns out if you think about light as a particle, those things that nobody could explain can be explained in a very straightforward manner. We now know that the people 400 years ago were asking the wrong question. They were asking, is it a wave or is it a particle? But we know now it's something different than either of those two things. It's like something that is both a wave and a particle at the same time. And so how does that work? So here I've drawn in a picture of a wave, and you can imagine that light is a wave. But what would it look like if light was a particle instead? It might be something like you just got like a hump that's traveling rather than this repeated up and down vibration. But the way we visualize light now is something that's like kind of the combination of the two. So rather than a full-on wave going all the way, you might have something that's just a few pulses that are traveling together. And so if you kind of zoom in, it looks like a wave. If you kind of zoom out, you'll see just sort of the envelope of the wave. The waves are kind of contained inside this region, and that region is traveling. It looks like a particle. And so this is kind of hand waving a little bit. This is not exactly how light waves are, but you can hopefully kind of visualize how something could behave in some ways like a wave and in other ways like a particle. And that's how light is. It's something that behaves both like a wave and a particle, usually one or the other depending on what kind of experiment you're doing. Now, in the previous chapter, we looked at all the ways that light can behave as a wave and how waves behave and what that means for the light that we analyze coming from astronomical objects. But that's not the complete picture. We also have to look at how sometimes light can behave like particles. And that's really what this chapter 4 is about. It's about how light behaves like particles. And we're going to continue looking at a field, or rather a tool, called spectroscopy. All the stuff that we were talking about in the previous chapter about blackbody curves, that was an aspect of this field called spectroscopy. But we're going to learn that not everything that emits light is a black body. Remember, a black body emits every possible color of the rainbow. But some things don't emit every possible color of the rainbow. And that's what we're going to talk about in this chapter. Now, in this picture here, you can see this is actually a picture of the sun's spectrum, but it's like blown up. Now you can see if this has got so, from the red all the way to the blue, it would be so long if I tried to do it left to right. So they kind of cut it into pieces and stack them together. So it looks kind of pretty. Now you can see there are actually lots of holes in this spectrum. If you zoom into the spectrum enough, you start to see some holes. And we're going to talk about what causes those holes. And it turns out to be a pretty cool thing. But let's get just to the basics. So here I have a situation. I've got an incandescent light bulb, and it turns out that incandescent light bulbs are pretty good black bodies. That is, they emit visible light. They emit a range of colors. If you get all the colors, you get white light. And so all the colors over the range are emitted by the light bulb, And so what we have is essentially black body radiation coming in, and we've got it focused, or actually we've got it collimated, it's called, with a lens. So all the rays of light are coming out parallel like a column, and then they pass through a slit into a prism. Now, we've already talked about this a little bit. Prisms will separate light into all the colors of the rainbow, which we can project onto a screen. And so if this is a black body, you see the spectrum has all the colors of the rainbow. And so that is characteristic of a black body spectrum. Now this whole setup here, this is what's called a spectroscope. And what a spectroscope does is it takes white light, or any light, and it splits that light into all the colors that are present in that light. Now here's the thing, if I have a light bulb, an incandescent bulb, it's going to emit all the possible colors and you'll get a black body spectrum. But if I take something like an element of, say, hydrogen, and I heat that hydrogen up hot enough so that it's glowing, the light it emits is not a black body. You don't get all the possible colors, you just get a few of them. And so here you can see there's a red, there's a green, there's some violets and some blues in there. You're not getting all the possible colors like you would from a black body. So hydrogen gas, if it's diffuse, if it's just not really super dense, and you heat it up so that it's glowing, it's going to give off what's called a discrete spectrum. And it's called a discrete spectrum because it's not continuous. This would be a continuous spectrum because all the colors are continuously touching one another and going from one end to the other. Here it's a discrete spectrum because you've got discrete individual colors. And this is what you call an emission spectrum. It's a spectrum that the thing giving off the light is actually emitting the light. Now, why does that matter? This turns out to be really, really important. It was discovered in the 1800s that every chemical, every element, every chemical compound gives off its own unique set of colors. And that unique set of colors is like a fingerprint. So here you see the emission spectrum from hydrogen gas. And you see there's a red, there's this teal, there's some blues and some violets in here. These are the colors given off by hydrogen. And so if I look at light coming from a gas that's emitting light, and I see just these colors, I can identify that as hydrogen gas. Like a fingerprint can identify a criminal at the scene of a crime, the colors that a particular chemical gives off can identify that color by using a spectroscope. And that's part of what we call spectroscopy. We can use spectroscopy, use a spectroscope, to identify what things are made of by the light that they're giving off. Here you see the spectrum of sodium, which has these two bright yellow lines. Here's helium, which has, like hydrogen, it's got a red, but it's a different red. See how this one's over a little bit? It would be at a different frequency, and we can actually measure the frequency and figure out how many vibrations per second that frequency is. Here it's got yellow. Hydrogen doesn't have any yellow, so the presence of the yellow here tells me that this is probably not hydrogen. And so it becomes like a puzzle to figure out, okay, I've got this color and that color, but not this other color. So I can figure out that this must be helium because these are the colors that helium gives off. Here you can see neon, which has got lots of reds and oranges, not much of the other colors. Here you see mercury, which has a different configuration. That is showing that every different element and every different chemical compound gives off its own set of colors. Now, what does that have to do with astronomy? We can look at the colors given off by a star and tell what that star is made out of. From billions and billions of light years away, we can find out the composition of the star. Now think about that. We've already seen we can determine how hot a star is by the light that it gives off. We've seen that we can determine what direction it's moving and how fast it's going by what light it's giving off. We can also tell what it's made out of. What chemicals does that star contain? Just by looking at the light, coming from that star. That's pretty incredible. All the things that we can tell about a star just by analyzing the light that's coming to us from it. It's pretty cool, right? Now there's another kind of spectrum called an absorption spectrum. And here's the idea. Let's say I take that hydrogen gas, but I don't heat it up, I don't make it glow. I just have a big ball of hydrogen gas, and behind that hydrogen gas I put a light bulb or some source of black body radiation. What does that mean that it's a black body? It means it's giving off all the different colors over that range. And so I've got all the colors passing through my hydrogen gas, and then I pass it through my spectroscope, and what I see is all the colors of the rainbow except the ones that the hydrogen would have given off if it were glowing. The hydrogen gas is absorbing the colors that it would give off if you heated it up hot enough to glow. I'll say that again. The hydrogen gas is absorbing the colors that it would emit if it had enough energy to emit light. So, if you heat the gas up, it'll emit only certain colors, but if you pass white light through that gas, it will absorb the colors that it normally would give off. And so if I look at this spectrum, I can see the gaps, and I can say, hey, those are the colors that hydrogen gives off. That means that my white light must have passed through a hydrogen cloud because there had to be some hydrogen somewhere to suck those colors out. And again, this is something that we can use to identify the composition of things in outer space, either by the light that they give off or the light that they absorb. And that is pretty darned cool. Now here we see sodium again, and we see two different versions of the spectrum. Which is the top? You guys tell me. Is this a emission spectrum or an absorption spectrum? You've got two bright yellow lines. This is an emission spectrum. This is the spectrum that sodium gas would give off if you heated it up hot enough. Now down here we see the full black body spectrum, except it's missing those two yellow lines that sodium gives off. So that means that there is some white light that had to have passed through a sodium gas that absorbed those two colors. Hopefully that makes sense, the difference between emission spectrums and absorption spectrums. Now, anyone that's had a class in physics, maybe in high school, will have learned about Kirchhoff from his work with electrical circuits. It's sort of the bane of physics students' existence when they study electricity. But Kirchhoff also did a lot to study light. In fact, he's the one that discovered that light that things give off is like a fingerprint that can be used to identify them. And he did a lot of studies about how these spectroscopy things work. And he came up with some rules that describe it. And here are the rules that he came up with. And so we have luminous. That just means glowing. So something's heated up enough so that it's glowing. Luminous, solid, liquid, or very dense gases will produce a continuous spectrum. Another word for continuous spectrum, all the colors together, that's a black body spectrum. And so luminous, that means glowing, solid liquids or gases that are dense gases, will give a continuous spectrum. Low density hot gases produce emission spectrums, and those are those discrete spectrums that we saw on the previous slide. And then continuous spectrum, that's all the colors of the rainbow incident on a cool, thin gas, produces an absorption spectrum. That's when the light passes through the gas and has the colors it would normally give off be absorbed by that gas instead of given off by it. So why do we get these individual lines rather than all the colors? And it has to do with the way that electrons work in the atoms. Now you probably learned in some of your science classes in the past that atoms are made up of protons, which are positively charged, neutrons, which are neutral, and electrons, which kind of flit around the nucleus of the atom, which is made up of the protons and the neutrons. And so here we can see a proton with an electron going around it. And the electron is confined to a particular region of space called the shell. And so here we can see the electron is in its shell orbiting around the proton. Now, if the electron gains energy, it can actually teleport to a higher shell. And so here the electron is, the first shell is no longer occupied by the electron because he's left home and he's gone up to this higher shell. Now, in order to get there, the electron had to absorb energy. Maybe some light shined on the atom and the electron absorbed some of that light, or maybe the atom got bumped and some of the kinetic energy, the energy of motion, got absorbed. However it happened, the electron absorbed some energy and it left its normal state and it went its normal shell and it jumped up to a higher shell. Now, what will happen is that electron will hang out in this higher shell for a little bit, and then he'll hop down to his home. He'll go back to where he normally belongs. And when he does that, he gives back the energy that he absorbed to leave home in the first place. And the energy of that gap, how far he has to jump to go from this shell to that shell, corresponds to a particular color of light. And so when he goes back home and he gives the energy back, it'll be emitted just as that one particular color of light. Instead of emitted as all the colors of light, it's just that one color of light. Now, we have this model that we learn in grade school that the electrons are orbiting the atom like the planets orbit the sun. But that's not really what's happening. What's actually going on is the electrons are kind of jumping back and forth. And so they're just hopping back and forth. And so this picture is showing all the places the electron has been over a certain period of time. And you can see, it's been all over the place, but there's this one ring here where he spent a lot of time. And so that would be the shell in which that electron can exist. But if that electron gets enough energy, rather than hopping back and forth or actually kind of teleporting back and forth within its own shell, it can actually teleport or hop up to the higher shell. And by the way, when the electron is in a higher shell, it's said to be in an excited state. When it's back in its home where it normally belongs, it's said to be in its ground state. It's fallen back to the ground. But anyway, the same idea is you have an electron in its particular shell, it gains energy, so it hops up to a higher energy shell, and then it returns home. And when it returns home, it gives that light back as a specific color. Now here we see a depiction of the hydrogen atom. Hydrogen typically has one proton and one electron, and these are some of the different shells that the electron can live in, and the corresponding energies that each of those shells contain. And so, if the electron is in the ground state here in this first shell, and it gains, let's say it gains 12.8 electron volts of energy, it would actually jump into this fourth shell. And so the electron could be flitting about here, then it gets this energy and it teleports there. Now, when it goes back home, it could actually go straight home, in which case it would give off a color of light corresponding to an energy of 12.8 electron volts. But it could actually stop off at its friend's house here. Instead of going all the way home, it could jump to this shell here, and then it would give off 12.8 minus 12.1, that would be 0.7 electron volts. And so that would be a different color that it would emit. It would emit a color corresponding to that energy gap. And so it could give a color from that jump. It could go from here to there, and that would be a different color. Or it could go from here all the way home, and that would be yet another color. And so there's a discrete number of colors that the atom can emit based on how many shells it has and based on the distance, the energy distance between each shell, how much of an energy gap there is between living in one shell versus living in another shell. And for hydrogen, there's actually a formula that tells you what the energy is in a particular shell. And you don't need to know what that formula is. I'm not going to make you use it, but just be aware that there is a shell that you can calculate. There is a formula that for hydrogen lets you calculate how much energy is in a particular shell. And so we can figure out what the difference is and use that to calculate the frequency of the light that jump or that transition would make.